Okay, this first video will be looking at the first problem on the test. I'll bring that up here. Okay, we see on this first problem worth 20 points that we have two rigid tanks that are connected via a valve, which is initially closed. The left chamber has a volume and has an equal molar mixture of CO2 and H2O. At a temperature, at a pressure. The right chamber, the right tank, has got a volume, has an equal mass mixture at a temperature and at a pressure. The valve is open and the gases are allowed to mix completely. After a period of time, the mixture temperature comes down to the surrounding temperature of 300 Kelvin due to heat transfer. So you'll notice that these aren't well insulated tanks, they're just rigid. And so after that period of time, we want to know what the final pressure is, what the amount of heat transfer occurred is, as well as the irreversibility associated with this mixing process. And we are asked to treat all the gases as ideal. So this is a situation where we have to, as before, we have to set up a mixture A, which is the left tank, a mixture B, which is the right tank, a mixture C, which is the combined into the combined volume. And so with that, we'll go ahead and launch the software. This is a closed mixing process, and so we'll be selecting the mixing process here under a closed system. And we were told that the gases in each of the mixtures will be a general gas mixture of ideal gases. And so the first thing we have to do is we have to specify what is mixture A. And mixture A is on an equal molar basis. And so when I select molar here, we then can say CO2 and H2O. So we have 1 mole of CO2 and we have 1 mole of H2O. And that then gives us our molar ratios associated with CO2 and H2O. Again, as we did before, I'm writing down or keeping track of these two mass ratios here. And because we're going to be using these mass ratios along with the total mass to then determine the mixture C. And so this is mixture A. We know that mixture A is a 2 cubic meters of volume, and the temperature of that side is 350 with a pressure of 200. So with this known, we know everything about that left-hand side. We also know that the total mass is 4.26 for that left-hand side. Now we're ready to then go back to determine mixture B, which is in the right-hand side. And in this case, it was an equal mass mixture of oxygen and nitrogen. And so we can keep it as kilograms, we can put in 1 there, we can put in 1 there, and we now have the 50-50 mass balance associated with mixture B. We then go to our second state, which we're going to specify as mixture B, and we know that there is 1 cubic meter, there is 1 cubic meter of volume, and we also know that the temperature is at 350. Wait a minute, okay, the temperature is at 400, and 300 kPa. And so with this in mind, then it determines for us that the mass in the right-hand side is 2.69, which is going to be divided in half based on the oxygen and the nitrogen. So we have mixture B. And now we're ready to go and determine mixture C. And mixture C then is, we can go ahead and put our information in here. We know that mixture C is 1/2 of mixture 2, the mass of 2. Nitrogen, it is 0.5 of mass 2, and we could add those two. And so basically that split it as 1.35 each because it was 1/2 on the mass balance. Now on the other two, the left-hand side, we say that the water itself, again I wrote down that the water had a mass balance of 2904 times mass 1, and the mass balance of the CO2 was 7096 times mass 1. And so we then can put those in again because it was an equal molar. We could add that. Now you'll see, yes indeed, they have the same mole fraction because they are equal molar. But now this is the makeup of the final mixture. The final mixture is its state 3. And what we know about the final mixture is that the temperature eventually gets down to 300 Kelvin. And we also know, because of the conservation of mass, we know that the two masses have to add up to be the third mass, and they all occupy the total volume. So we've done this a number of times. And so with the mass and the volume determined, that gives us the specific volume of the mixture. We know the temperature, and that's our two independent thermodynamic properties, and it's able then to determine that the final pressure is that. Okay. Now, in this particular case, then we want to go to our process panel. And basically our process panel, we recognize that we have state 1 here and state 2 here going to state 3. Oops, to state 3. And so, let's see. I need A and B. This should say C. I'm going to initialize this. And so it's 1 and 2 and going to 3. And basically what this meant was that I have to go back, and when I specify state 3, that's my mistake. State 3 is actually mixture C. Okay, so so again we have the temperature and we have the specific volume, and so we recalculate, and yes indeed now we have mixture C, and we then can go to the process panel, and you see now A and B turn into C. We assume that there is no work because of the rigid nature, and we see that the heat transfer that has to occur is minus away from the system 381. We also know that in order to determine the irreversibility, which is related to this S-Gen 1, we have to make sure that we have the proper value of the boundary temperature. And that proper value of the boundary temperature would be the final temperature, and that was specified. That would be obtained from the heat transfer, the final condition. So heat transfer occurs because of the 300 boundary temperature. So we do a super calculate, and that shows us that the S-Gen is equal to 1.41. It also shows that the heat transfer is this amount, and we were also asked for the final pressure. The final pressure is going to be in state 3, which is this amount here, 189. Now if I went back to my I/O panel, I could have it calculate for us the irreversibility, which is just S-Gen 1, process 1, times the temperature B1. That was the boundary temperature. So this then calculates for us then what the irreversibility is. It's 425.9. And that then finishes up this particular problem.